Okay, so now that you know what equilibrium is and how the graphs and everything look, now we can move on to calculations for equilibrium. Now, in equilibrium calculations, we use a table, which is what we call this Rice table or Rice QE table. Okay, now each of those letters stands for something. If you look here, the R in this stands for the chemical reaction, so the reaction itself. So the first step is to always write the chemical reaction, and you need to make sure that that chemical reaction is correctly balanced, because balancing it is going to help us do the calculations. If it is not balanced, or if it's not balanced properly, all of the calculations will not make sense afterwards. Right, the R in this table stands for the initial moles. Now, initial moles means what we are starting off with, how much reactants we are starting off with. Now, normally they will give you the initial moles of the reactants and the products, because you don't have product at the beginning of the reaction, obviously, because the reaction didn't yet start. So the product initial moles will be 0. Unless they give you moles for product, then you will have it. But if they don't give it to you, the initial moles for products will always be 0. Now, we're talking about moles here, but sometimes you can just have all of this information in concentration instead of moles. Sometimes you have it in moles, and at the end you convert it to concentration. We'll see later in examples. And sometimes you can just have concentration, and that way you don't need to have moles. You can just work with concentration throughout this table. Then the C here stands for the change in moles. Now, obviously, in the reaction, you have reactants, and the reactants turns into products. And as that reaction is happening, you're going to have chemical equilibrium being reached after a while. So that change is the change that is happening from the beginning of the reaction until before you reach equilibrium. And this change is always in terms of x. So we'll see later on, it's almost like doing a maths equation. It's in terms of x. And then you have the Q. Now Q stands for quantity moles at equilibrium in moles. Now this is the moles that you have at equilibrium. It's not the initial moles, it's not the change in moles, it's the moles at equilibrium, which is almost like at the end of the reaction, because from now all of the reactants are going to stay at a constant concentration. Now, if I didn't mention this before, if I write EQ/M, this actually means equilibrium. So it's a short way for writing equilibrium. So if you see this EQ/M, just know it is equilibrium. Right, and then lastly you have the E, and E stands for equilibrium concentration. So far in the beginning we've been dealing with moles, moles, moles. When you're coming to E, now you're dealing with concentration. So the E that you have actually comes from Q. So from Q you have quantity of moles at equilibrium. Now when it comes to E, you're going to use the quantity at equilibrium, and you're going to take that moles and convert it into concentration, and that's what is going to give you E. And the way you do this is by using the formula which you're all familiar with. It's C is equals to N over V. So you're going to use this formula, and you're going to use the moles, and they will give you the volume, and then you will calculate the concentration. So this table, first of all, you need the reaction. Second of all, the initial moles and the reactants, they will give it to you. For products, initial moles is normally 0. Then you have change, which is in terms of X. You have quantity of moles at equilibrium, and then you have the actual equilibrium concentration, which you can get from this formula if it was not directly in concentration from the beginning. Okay, now we're going to go on to examples, because that's the best way you can understand things. And there is a few examples in the textbook. I'm only going to go through 3 of them, but I want you to go through all of them. The more you do, the more easier it will become, and then you won't even have to think twice about it. Right, let's look at example 1. You have a mixture of 5 moles of hydrogen and 6 moles of iodine is placed in a sealed container of 2 decimeter cubed. Now when you see cubed, it means volume. So just keep in mind the volume of this container is 2 decimeter cubed. At a temperature of 458 degrees Celsius, don't worry about the temperature. The balanced chemical equation for the reaction is H2 plus I2, giving you 2HI. Now, since you're seeing this reversible arrows here, this shows you that this reaction is reversible, and because it's reversible, it's going to have or involve chemical equilibrium. Right, equilibrium is reached in a certain time frame. At equilibrium, there are 4 moles of HI. HI is the product in the container. Calculate the concentrations of H2, I2 at equilibrium, which is their equilibrium concentrations. Right, so the first step is, if you have no idea what to do, just follow the Rice table. Right, so the first step is you will write the chemical reaction. Right, now you can draw a table like this where you label it rice, and then don't forget the Q, rice, QE, and then make columns for each of the reactants and products. So here you have a column for H2, a column for I2, and a column for the product, which is HI. Right, and just keep in mind the volume is 2 decimeter cubed. Now, the next step after you write the reaction, which is written here already, and it's already balanced for us, the next step is to write I, which stands for initial moles. Right, so I is going to be in moles. Right, now they gave us the moles of this, so we don't have to stress about it. They said in the beginning you had 5 moles of H2. So we're just going to write 5 here for hydrogen. And they said we have 6 moles of iodine. So we're going to put a 6 here. Now, because HI is the product and they did not mention anything about the product, we will assume that in the beginning of the reaction we don't have any product, so the product's moles will be 0. So just remember, if they do not give you the amount of product in moles or concentration, it means in the initially with the I, the product will be 0. Right, then we're going to have C, which is standing for change. Now this one is in terms of X. Okay, now the way we do this is by using the coefficients in the correctly balanced chemical equation. Now if you look at this formula, can you see that you have H2 and the coefficient is 1, so it's just a 1, and then you have I2, the coefficient again is 1, and then you have HI, but now the coefficient is 2. Now, we're going to use those coefficients as coefficients of X, and we're going to realize that in a chemical reaction, reactants always become less because you're using it up to make products, and products always become more because you're forming products. So just remember that reactants always decrease and products always increase, and because of that, when we show reactants in terms of X, we show it with a minus, and when we show products, because it increases, we show it with a positive. So when you're dealing with C, you're going to have H2 and H has a 1 in front of it, right? So it's going to be 1x, but I'm just going to write x because you know that stands for 1. And because it is a reactant, I'm going to put a minus in front of it because reactants always decrease, so the minus shows it decreases. And then for I2, the same thing. The coefficient is 1, so it's just going to be 1x. And also it's a reactant, so I'm going to put a negative sign. Now, when it comes to the product, this product has a coefficient of 2, so I'm going to say 2, and then it has to have an x, so it will become 2x. And since it's a product and product increases, I'm going to put a positive. So when it comes to the C in this table, you do it in terms of X. The coefficient of X will be the same coefficient that is in the chemical equation that is balanced, and all reactants will have a negative sign and all products will have a positive sign. Okay. Right, and then they also mentioned to us that at equilibrium, you have 4 moles of HI. So they're telling us at equilibrium, there's 4 moles of the product. They're not saying initially or at the end there's 4 moles, they're saying at equilibrium. Now equilibrium is Q, the moles at equilibrium. So because they said there's 4 moles of HI, I'm going to put a 4 here because that's how many moles of HI we have at equilibrium. Right, now we need to actually find out what is this X, because right now we just have an X, we don't know what X actually is. Right, so the way we do that is we're going to look at this table and look at which reactant or product has enough information for us to determine X, and that will be the product or reactant which has all of I, C, and Q filled in. Now, if you look here at the table, for H2 and I2, we only have initial and we only have change. We don't have anything at equilibrium. So we cannot use H2 and I2 to determine X. But if you look at HI, we have the initial, which is 0. We have change, which is plus 2X. And we have Q, which is moles at equilibrium, which is 4. So because we have all of these 3 columns filled in, we can use HI, the product, to determine X. Now the way we do that is all you have to do is say the initial plus the change is equal to the moles at equilibrium. So it's basically the first number plus the second number. So you're going to add the two, and that is equal to the equilibrium number. So then we're going to write this, so you can do this on a separate page or even on the same place. So you're going to say 0, which is initial, plus change, which is 2x, is equals to whatever is Q, and that is 4. Now we actually have here a proper chemical equation, and from this equation we can find out what X is. Now you guys know how to do that. It's just simple maths. To work out X, you're going to obviously solve for X, and from here you will see that X is equals to 2. Right, now we actually know the value of X, and so, because we know the value of X now, we can take this value of X and substitute it into these parts where we have X. Right, so let's go back to the table. So you have HI here, and then you have minus X. Now since we determined that X is equals to 2, this actually means it's going to be minus 2 because it's minus X, so that's minus 2. And then here we have also minus X, and X is 2, so again it will be a minus 2. Now that we know the initial moles of the reactants and we know the change, we can work out the equilibrium moles. So we're just going to say initial minus this will give you this. So we're going to say 5 minus 2, which will give you 3, and this is how many moles you have left over at equilibrium for H2. And we're going to do the same thing for I2. So you're going to say 6 minus 2 is equals to 4, and that's how many moles of I2 you have at equilibrium. So basically you just need to fill in the information in the table, and whichever one you have the most information for, you will use that to determine X. And then once you have X, you can use the rest of the reactants or products which you don't have enough information for, and you can substitute X, and that will give you the equilibrium moles. Right, now that we have the equilibrium moles, we just need to work out E, which is the concentration at equilibrium, and for this we're going to use the formula C is equals to N over V. Now the equilibrium concentration, this one is moles. Right, all of them are actually moles. So we're going to say moles divided by volume. And remember in the beginning, they gave us volume, which is 2 decimeter cubed. So we basically have to take all of the moles divided by 2, and that will give you the volume. Now, when we are working out E, remember E comes from Q. So whatever moles you have at Q is what you're going to use to work out E. So we're not going to use initial, we're not going to use change, we are going to use this third row, which is Q. So we're going to start with H2. H2 you have 3. You're going to divide it by the volume, which is 2. So 3 divided by 2 will give you 1.5. And this obviously is concentration, so the units will be moles per decimeter minus 3. Right, and then we're going to do the same thing here. So it's going to be 4 divided by 2, which will give you 2 moles per decimeter minus 3. And then we're going to do the same thing for the last one. It's 4 again. So 4 is the moles divided by the volume, which is 2. And that will again give you 2 moles per decimeter minus 3. So this is not really very complicated. It's just that you have to work systematically, and then you'll get used to it once you do enough of it.